Hi, my name is Cedric Renet, and along with Paul Strohmeyer, we're going to present PolySense, an accessible process that makes fabric smarter. This presentation will be chronological from the original problem to the first solution, followed by a few unexpected discoveries and opportunities for the future. Let's start with the initial motivation. This project was born at DataPolet, a hackerspace collective focused on e-textiles, such as this matrix pressure sensor. This sensor uses two kinds of materials. First, let's discuss the conductive fabric. On the right, we can see horizontal stripes used to sequentially power the sensor for rasterization. On the left, we see the vertical stripes. They are connected to the analog front end of the electronic circuit, which reports the measures to a computer. In the middle, you can see a darker fabric. This is the piezoresistive material. It changes its resistance when someone presses it. This material is expensive, about $200 per square meter, and it became harder to get over time. But what is piezoresistivity anyway? We illustrate it here as a layer of free conductive particles. When they are pressed together, the overall conductance increases or the resistance decreases. So we tried to make our own coating ink with silver, copper, or carbon particles, and we were never really satisfied. We realized that we didn't really understand the material. Fortunately, I met our collaborator, Anna Batista, and I spent a week in her material science lab. And after various analyses, such as Raman spectroscopy, we understood better what could be in the reference material. And everything became much clearer. Thanks to this expertise, we found various solutions to implement the piezoresistive behavior. And then we worked hard to design a simple process that you can replicate in your kitchen. We ended up needing only two chemicals, a monomer called pyrrole and iron chloride, which is also used for PCB etching. So it's very common. Here, we use the magnetic stirrer to mix the textiles with the chemicals, and we tuned the process to obtain a pressure sensor in about 1 hour. Paul has a comment, I think, here.
Yeah, well, we prepared a bunch of applications, and the point of them is to give you an idea of what can be done with polymerization. But I think an important take-home of these applications is that we're not presenting something which is finished now. So we're not at the end of a process. We're kind of sharing actually the beginning of a process. And you'll notice the examples that Cedric is going to show in a moment, they're all either examples of work that we have done, since getting this paper published, or of ongoing projects that we're working on right now. So this is something that we're actively using in our research and in our design and artwork.
As Paul said, in these applications, we did a few things. Here we augmented off-the-shelf gloves to augment 3D models here for a virtual hand. As all of our projects, this one is on GitHub. It's available for you to play with. For the Augmented Humans conference, we showed that off-the-shelf kinesiotape can be augmented for various on-skin interfaces, including this linear slider that we can see here. Kinesiotape is made of textile and skin-compatible glue. It can be found in most pharmacies and supermarkets. After the small embedded applications that we just saw, we might wonder, how does this process scale? Here, we can see an installation that uses several meters of functionalized fabric. It is still working perfectly after many weeks, exhibited in a museum in France, where the fabric was touched every day by visitors. So the process is reliable over time. In this other artistic application, we polymerized feathers and used them as capacitive sensors for a sonified installation. Both installations were nominated for a secret Austrian festival, and they might be exhibited there depending on the coronavirus evolution. PolySense focused on e-textiles, but we functionalized many other materials. And almost anything porous or fibrous works. Last summer, Hannah also augmented a pair of leggings. She's one of our co-authors. And she controlled her presentation slides at CCC. This is the biggest hackerspace congress in the world, about 70,000 people last winter and 5,000 last summer. Thanks to the warm conditions, we realized that our process can also make a great humidity sensors or sweat sensor. Finally, PolySense can also be used for custom actuators. As anything resistive, this polymerized glove hits when electrified, and as anything resistive, temperature affects its resistance. So we characterize the resistance variation as a function of temperature. And we observe that heating can be safely controlled with a feedback loop, thanks to the collocated sensing and actuated possibility. So you just saw a few possibilities that we deployed in various festivals and conferences. Now you might want to do your own polymerization. The paper describes the process, but let's do a step-by-step together. Firstly, we use a bit less than twice the water needed to soak all the fabric, all the material that you want to polymerize. Secondly, mix it with the monomer. Again, it's pyrrole. Then soak the fabric and mix it for about 10 minutes. Finally, add the oxidizing agent. Again, it's iron chloride. That's what triggers the in situ polymerization. For piezoresistive sensors, keep mixing for about half an hour. And for capacitive sensors, about 2 hours. A longer polymerization improves the conductance, but synthetic materials may need a bit more time in general. So polymers are just chains of monomers. But why is this particular polymerization called in situ? Well, because we first soak the fabric with the monomer, and then we trigger the polymerization. So each fiber gets merged with the chains that are formed in place. In a way, we can see it a bit like a molecular level dyeing process. So this polymerization mostly creates chains of carbon. It explains why the results are so dark, but it also explains the electrical conductivity. We characterized this conductance, and Paul will discuss it now.
Okay, just give me a second to share my screen. So on some level, what we're doing is so much more versatile than anything you can get commercially that we didn't really care specifically, is our material a better pressure sensor, or how it compares to existing things. But still, we thought that you guys would be curious how it does compare. So here's some examples. So it should also be noted that depending on which fabric you're using to polymerize, the results vary greatly. And as Cedric was saying, time is also a factor in how the final results look. But in this graphs, on the x-axis, you see 3 finger presses. So for each of these fabrics, we press it with a finger 3 times, and we recorded force. And then we recorded the corresponding resistance. And we also plotted these against each other. And you can see that all of them, the commercial one and ours, they all have quite some hysteresis. Some of ours have more hysteresis, or appear to have more hysteresis than the commercial material. But they're more or less similar in how they behave. But the interesting part is, which we were quite happy with, that the dynamic range that we can achieve is typically higher than those of commercial materials that we could buy. But having said that, that's not really the cool part about this process. That's not why it's so interesting. So let me talk about design methods, because in a way, talking about these large pieces of fabric is like saying, copper is really great for electronics, which it is, but it is once you give it structure. So without structure, well, there's not really much you can do with it. And we looked at methods inspired kind of by traditional craft of working with fabric. So one of these processes is shibori, or more commonly known, well, it's originally called shibori in Japan, and today we know it as tie-dyeing. And you can create all kinds of patterns. People get really creative with this. One of the interesting things about tie-dyeing is, well, you can create repetitive patterns, but you can also create gradients. So the sample on the right-hand side, it was rolled up before it was tied and dyed. And the layers that are furthest down have the highest resistance. So going from top to bottom, M2 to M3 to M4, the resistance decreases as you go to the outside of the wrap that we made. Now, in the clip that I showed before, we weren't only tie-dyeing fabric, we were also tie-dyeing thread. And the reason why this is interesting is you can create a pattern in thread, and then you can weave it. And if you design it correctly, you can have the weave have the specific shapes that you intended it to have. We didn't explore this very far, but we have friends in Berlin, Studio Hilo, who are creating devices that create custom thread, and they have software for creating custom patterns out of their custom thread. And we think that's a super interesting way to explore for pushing e-textiles further. And then the method we actually use the most is from Indonesia. It's called batik. And here you basically use hot wax to create a wax resist. You put wax everywhere where you don't want the polymerization process to happen. And again, this is a method that can create all kinds of patterns. In this example, we kind of played with this idea of creating resistors where we want them. And we kind of looked at, you see there's two large areas connected through small channels. And you see that if you measure resistance between two areas with which are connected through a thick area, it's orders of magnitude less resistance than if the electricity has to kind of find its way through the small channels we created here. So basically, we can create resistors of the resistance that we want by doing the design well. And we also use batik to, well, to take a functional fabric, an off-the-shelf fabric, and basically treat it like a PCB, add a wax layer and etch away everything where it should not conduct. The reason this is super interesting is you can create a fabric with some kind of conductive, highly conductive pattern, and then you can polymerize that. And this kind of allows you to implement a full circuit in fabric. So this is a sample we made. The idea was kind of to have this be like kind of a fabric game controller of sorts. I just wanted a bunch of input methods and a piece of fabric. And in the middle, you see a vertical and horizontal black stripe. You could think of these as a differential stretch sensor. So if you can imagine the way I have laid it out here, if you stretch it horizontally, the resistance that, or the voltage you measure at the analog input that I indicated in white would drop. And if you stretch it the other way, the voltage would increase. And I thought that you would also kind of like wrap up the edges and then have two pressure sensors. So here we're kind of back in this layered design that we've seen a lot of, but you can measure the resistance from A to B through the piezoresistive material in C. So these are just ways of kind of implementing a lot of things which usually would be circuitry directly into the fabric. And this is where the real promise of the methods we're showing in this paper lies. So before I conclude, I just kind of want to touch on some high-level points which we thought were important. And the first, I'm kind of quoting Cedric here. He kept saying this throughout the project. We need to visit our neighbors. And basically, if you look at the authors, we all have very different backgrounds, contexts, ways of working and thinking, and none of us alone would have come up with this. And combining knowledge and approaches from different domains really allowed us to push the boundaries of this project. It's not always easy, but it's definitely worth it. The other idea, and I'm stealing this from Make, if you can't open it, you don't own it. And even more, if your intention is to design a product and you don't understand parts of the materials you're using, you don't really have a product. You're dependent on suppliers who are hiding critical information from you. So let's say the supplier doesn't supply the material anymore, or they change the formula and it doesn't work anymore. You go to a new supplier and say, hey, can you build this for me? And they say, yeah, sure, just tell us the formula to use. You're not in a good place. That was the problem we were originally addressing. But in working with our process, we realized that there's something much more profound happening here. And I'm quoting Irene Posch here, who had this beautiful slide at TI a couple of years ago saying tools are not neutral. The same is true for materials. So the material, the piezoresistive material that many of us know, this fixed felt-like material, it inspires a certain way of using it. So the original matrix design that Cedric showed at the very beginning is a very typical design. You will see variations of this a lot, of kind of layering this felt material in between two conductive materials. And in this way, the material you're working with shapes the outcome. And by providing a generic process, our designs are no longer constrained in that way. We can really freely reflect on them. And this is reflected in the diversity of examples that Cedric showed at the beginning. And to me, that's kind of the real strong point of this project. Finally, what you see in the middle here, and I'm quoting Hannah, our co-author, that's her version of the open hardware logo. And it symbolizes a fruit, and in it, it has seeds. So what we're trying to do here is we're trying to not only share the fruit, but we're sharing the fruit with its seeds. Before I conclude, I'd like to thank Anna Baptista, Hannah Perna-Wilson, Marc Tessier, Bruno Fouchard, and Jürgen Steimle for our collaborators on this project. Cedric and I want to thank them. And with that, I conclude our presentation, and I'd be happy to take some questions. Thank you.